To calculate conduit fill percentage when using Romex cables, firstly determine the trade size of the conduit. This refers to the diameter of the conduit, typically measured in inches. Common sizes include 1/2 inch, 3/4 inch, 1 inch, and 1 and 1/4 inches. Secondly, calculate the area of the conduit. This is done using the formula pi times r squared, where r represents the radius of the conduit. For instance, if you're using a 1-inch conduit, the radius is 0.5 inches. Therefore, the area would be approximately 3.14159 times 0.5 squared, which equals approximately 0.79 square inches. Thirdly, determine the area of each Romex cable you intend to use. To do this, consult the Romex specifications to find the diameter of the cable. Then convert the diameter to a radius and apply the same area formula pi times r squared. For example, number 14 American wire gauge, or AUG, Romex has a diameter of 0.259 inches. The radius would be 0.1295 inches. So the area would be approximately 3.14159 times 0.1295 squared, resulting in approximately 0.53 square inches. Fourthly, calculate the conduit fill percentage. This involves dividing the total area of all the Romex cables by the area of the conduit. For example, if you're installing two number 14 AWG Romex cables in a 1-inch conduit, the calculation would be fill percentage equals 2 times 0.53 divided by 0.79, which equals 0.135, or 13.5%. To determine the maximum number of Romex cables that can be installed, you can use the following formula: maximum number of Romex equals conduit fill percentage times conduit area divided by the area of each Romex cable. For instance, with a 1-inch conduit having a fill percentage of 31%, the calculation would be maximum number of Romex equals 0.31 times 0.79 divided by 0.53, which equals approximately 4.6. Consequently, this conduit can accommodate up to 4 number 14 AWG Romex cables. It's crucial to note that the conduit fill percentage should not exceed 40% for raceways used for circuit conductors, adhering to the National Electrical Code, or NEC. Always verify local building codes to confirm the maximum allowable conduit fill percentage. Additionally, ensure sufficient space within the conduit for bending and pulling wires. Consider these factors when calculating conduit fill. Firstly, conduit size. The internal diameter of the conduit dictates the available space. Secondly, wire size. The cross-sectional area of each wire or cable contributes to the overall fill. Thirdly, fill percentage limitations. The NEC specifies maximum fill percentages to ensure proper heat dissipation and ease of installation. For single conductors, the fill percentage is typically limited to 53%. For 2 conductors, it's limited to 31%, and for 3 or more conductors, it's limited to 40%. Fourthly, conductor types. Different types of conductors, such as THHN, THWN, and XHHW, have varying insulation thicknesses affecting their overall diameter and contribution to conduit fill. Fifthly, conduit type. Rigid metal conduit, or RMC, electrical metallic tubing, or EMT, and flexible metal conduit, or FMC, have different internal diameters for the same nominal size, influencing the available space. Sixthly, the number of bends. Excessive bends in a conduit run can make pulling wires more difficult and may require reducing the allowable fill percentage. Seventhly, expansion and contraction. In installations subject to temperature variations, consider the expansion and contraction of both the conduit and the conductors. Eighthly, derating. When multiple current-carrying conductors are installed in a conduit, the ampacity of each conductor may need to be derated to prevent overheating. Ninthly, local codes and regulations. Always adhere to local electrical codes and regulations, which may impose more stringent requirements than the NEC. Tenthly, future expansion. Plan for future expansion by leaving some spare capacity in the conduit to accommodate additional wires or cables. When dealing with multiple conductors in a conduit, There are several considerations to keep in mind. Firstly, heat dissipation. Conductors generate heat when carrying current, and closely packed conductors in a conduit can lead to increased temperatures. The NEC specifies unpassed heat dirtying factors to account for this effect, reducing the allowable current carrying capacity of the conductors. Secondly, voltage drop. Long conduit runs can result in voltage drop, especially with smaller conductors or high current loads. Proper conductor sizing is essential to minimize voltage drop and ensure adequate voltage at the load. Thirdly, insulation type. The type of insulation on the conductors affects their temperature rating and suitability for use in different environments. THHN and THWN conductors are commonly used in conduit installations due to their high temperature ratings and moisture resistance. Fourthly, conduit material. The material of the conduit, such as steel or aluminum, can affect its heat dissipation properties and its ability to protect the conductors from physical damage. Fifthly, pulling force. When pulling conductors through a conduit, excessive pulling force can damage the conductors or the conduit itself. Lubricants and proper pulling techniques can help reduce friction and minimize the risk of damage. Sixthly, conduit fill calculations. Accurate conduit fill calculations are essential to ensure that the conductors can be installed safely and in compliance with the NEC. These calculations take into account the size and number of conductors, as well as the internal diameter of the conduit. Seventhly, grounding. Proper grounding is essential for electrical safety. Grounding conductors should be installed in the conduit along with the circuit conductors to provide a path for fault current to return to the source. Eighthly, bonding. Bonding refers to the connection of metallic parts of the electrical system to create an electrically conductive path. Bonding is essential for minimizing the risk of electric shock and ensuring proper operation of overcurrent protective devices. Ninthly, support. Conduits must be properly supported to prevent sagging or damage. The NEC specifies the maximum spacing between conduit supports, depending on the size and type of conduit. Tenthly, labeling. Conduits should be clearly labeled to identify the circuits they contain. This helps to prevent confusion and ensures that maintenance and repairs can be performed safely and efficiently. In practical applications, several factors can influence the choice of conduit size and the number of conductors installed within it. Firstly, the type of occupancy. Different types of occupancies, such as residential, commercial, and industrial, have different electrical requirements. Commercial and industrial occupancies typically require larger conduit sizes and more conductors than residential occupancies. Secondly, the load requirements. The amount of power required by the electrical loads determines the size and number of conductors needed. High power loads, such as motors and heating equipment, require larger conductors and may necessitate larger conduit sizes. Thirdly, the distance to the load. The distance between the power source and the load affects the voltage drop and the required conductor size. Longer distances typically require larger conductors to minimize voltage drop. Fourthly, the environmental conditions. Environmental conditions such as temperature and humidity can affect the performance and longevity of electrical conductors and conduits. In harsh environments, corrosion-resistant materials and special installation techniques may be required. Fifthly, the accessibility of the conduit. The accessibility of the conduit affects the ease of installation, maintenance, and future modifications. Conduits that are buried or concealed behind walls may be more difficult to access and may require larger sizes to accommodate future changes. Sixthly, the cost. The cost of materials and labor is an important consideration when selecting conduit sizes and conductor types. Larger conduit sizes and more expensive conductors can significantly increase the overall cost of the electrical installation. Seventhly, the aesthetics. The appearance of the electrical installation may be a factor in some applications. Concealed conduits and flush-mounted boxes can provide a more aesthetically pleasing appearance than exposed conduits and surface-mounted boxes. Eighthly, the safety requirements. Safety is paramount in electrical installations. All work must be performed in accordance with the NEC and local electrical codes to ensure the safety of people and property. Ninthly, the future needs. It is important to consider future electrical needs when designing an electrical installation. Leaving spare capacity in conduits and panels can make it easier to add new circuits and loads in the future. Tenthly, the coordination with other trades. Electrical work must be coordinated with other trades such as plumbing, HVAC, and carpentry to avoid conflicts and ensure a smooth and efficient construction process. When working with Romex in conduit, there are some specific considerations to keep in mind. Firstly, protection from physical damage. Romex, also known as non-metallic sheath cable, is designed for use in dry, interior locations. When run in conduit, it is protected from physical damage, such as abrasion and impact. Secondly, protection from moisture. While Romex is not designed for use in wet locations, running it in conduit can provide some protection from moisture. However, it is important to use watertight fittings and seal any openings in the conduit to prevent water from entering. Thirdly, compliance with NEC. The NEC permits the use of Romex in conduit under certain conditions. It is important to consult the NEC and local electrical codes to ensure that the installation complies with all applicable requirements. Fourthly, conduit fill. When running Romex in conduit, it is important to follow the conduit fill requirements specified in the NEC. The number of Romex cables that can be installed in a conduit depends on the size of the conduit and the size of the cables. Fifthly, pulling Romex through conduit. Pulling Romex through conduit can be more difficult than pulling individual conductors. It is important to use a lubricant and avoid sharp bends in the conduit to minimize friction and prevent damage to the cable. Sixthly, supporting Romex in conduit. Romex must be properly supported within the conduit to prevent sagging and strain. The NEC specifies the maximum spacing between supports. Seventhly, using appropriate fittings. Use fittings that are specifically designed for use with Romex and conduit. These fittings will provide a secure connection and protect the cable from damage. Eighthly, avoiding overheating. When running Romex in conduit, it is important to avoid overheating. Direct the ampacity of the Romex if necessary to ensure that it does not exceed its temperature rating. Ninthly, grounding. Ensure that the conduit is properly grounded to provide a path for fault current to return to the source. Tenthly, labeling. Label the conduit to identify the circuits it contains. This will help to prevent confusion and ensure that maintenance and repairs can be performed safely and efficiently. Understanding the NEC tables relevant to conduit fill is crucial for electrical installations. The NEC provides tables that specify the maximum allowable fill for different types of conduits and conductors. Firstly, Chapter 9, Table 1. This table provides the dimensions and areas of various types of conduits, including rigid metal conduit, electrical metallic tubing, and flexible metal conduit. These dimensions are used to calculate the conduit fill percentage. Secondly, Chapter 9, Table 4. This table provides the dimensions and areas of various types of conductors, including THHN, THWN, and XHHW. These dimensions are used to calculate the total area of the conductors in the conduit. Thirdly, Chapter 9, Table 5. This table specifies the maximum allowable fill percentage for different types of conduits and conductors. The fill percentage depends on the number of conductors in the conduit. Fourthly, Chapter 9, Table 5a. This table provides the maximum number of conductors allowed in various sizes of conduit based on the conductor size and type. Fifthly, Note 9 to the tables. This note provides additional information and clarification on the conduit fill requirements. It specifies how to calculate the fill percentage for different types of conductors and conduits. Sixthly, Annex C. This annex provides examples of conduit fill calculations. These examples can be helpful in understanding how to apply the NEC tables and requirements. Seventhly, Table 310.15b16. This table provides the allowable ampacities of insulated conductors rated up to 600 volts, 60 degrees Celsius to 90 degrees Celsius in free air. Eighthly, Table 310.15b17. This table provides adjustment factors for more than 3 current carrying conductors in a raceway or cable. Ninthly, Table 310.15b18. This table provides ambient temperature correction factors for ampacity. 10thly, Article 344. This article covers the requirements for rigid metal conduit, including its installation, support, and grounding. Remember to always consult the latest edition of the NEC and local electrical codes to ensure compliance with all applicable requirements.